Okay, thanks. So a couple of things before we start. At this point, I'm assuming you all have a copy of the book, one way or the other. I received an email by one of you who's still waiting for the shipment of the book. I know that it's in stock on Amazon. I just checked yesterday. It was available. But if you don't have the book for any reason, the library has, I think they only have one copy or so, and it's out. Three? Yeah, it's on hold. But anyways, I have only one copy myself, so I cannot really share it. But if you, again, come to office hours, you have 3 hours every week. You can sit there and consult the copy if you really don't have the book. So that's the most I can do. Or share it with your colleagues until you get your copy. But again, Amazon will be probably the best. So I also posted solutions for Chapter 2. You have all the solutions for the problems in the book. Do solve them yourself first. Don't even look at that PDF before you start solving the problems. That would be like watching TV. You're passive and just read. You don't do it, and that's not a good idea. And I would really like to start seeing people at office hours. Unless you're attacking the problems, you have no issues. If that's the case, that's great, but I don't know. That's not usually the case. So start coming. This is where we left off last time, and I redrew the picture here. I hope it's... I don't know if it's better than last time, but we were addressing cylindrical and spherical coordinates. We were done with the cylindrical ones. We need to finish with the spherical coordinates. And so we defined a Cartesian coordinate system fixed to a reference frame A, and then we defined two other reference frames. Reference frame B, which is basically the plane OPQ, which is rotating about the axis z, and in that frame we defined the coordinate system ER, E theta, EZ, and those associated with that we have theta and little r, and those were r and z, of course, and those were our cylindrical coordinates, and we computed the velocity of point P as seen by an observer fixed in A, and the acceleration of the same point as seen by an observer fixed in A using those coordinates. So we're done with those. We were finishing up the case of spherical coordinates, where we define now basically the same reference frame, B, that is now allowed to rotate about the E theta axis. So we introduce an additional angle phi, and now our coordinates are rho, theta, and phi, and our coordinate system is UR, U phi, U theta in this order, UR, U phi, U theta. U theta is the same as E theta, rule of thumb. Every rotation generates a common axis. You use the one of the axes of the previous coordinate system. And one of you came up last time after lecture. I think the direction of E theta was not clear. So E theta is a unit vector perpendicular, again, to the plane OPQ. I hope everybody can see that. So as this plane rotates, because P is moving, E theta remains perpendicular to that plane. You know, things in 3D are always hard to visualize, and that's why I always suggest that you break it down into planes. Look at the planes for each rotation. Okay, and without reinventing the wheel, we got already to the point of writing, I believe, the angular acceleration of C as seen by an observer in A. We used the rule of the addition of angular velocities, and we also had to do a coordinate transformation. The final result was the following: theta dot cosine of phi UR minus theta dot sine of phi U phi plus phi dot U theta. Does it match with what you have? It should match, right? Okay. Well then, same story. I want to compute these two quantities, but now I am an observer fixed in C. So the first one, velocity of P in A, is d dt in A of r, the position of the point. If I am in C now, the transport theorem tells me that this is d dt in C of r plus omega Ca cross with r. What is r? Remember, I'm now sitting in that. That's rho UR. And so this first derivative is rate of change, ddt of r in C. In C, I don't see UR changing, so that's rho dot UR. And then we start having huge cross products, which we have to do. This is, again, bookkeeping. So the omega AC cross with R is, and this is the simple one, with the acceleration will become even bigger, theta dot cosine of phi UR minus theta dot sine of phi U phi plus phi dot U theta cross with R, which is rho UR. Let me erase this and move up here. I really don't want to touch that picture there. So we're gonna, what we get from this cross product will be added to rho dot UR to get VP in A. Well, let's do that cross product. What's one by one? First one is obviously 0, UR cross with UR. Then we have U phi cross with UR. Here we go. U phi cross with UR is minus U theta, so that minus goes away. And you have rho theta dot sine of phi U theta. Do we agree? And then we have U theta cross with UR. That's U phi. So I have rho phi dot U phi. So this is what I get here. Okay? And so when we put it all together, the velocity of P in A, let's go in order here, it's rho dot UR, then phi is my second vector of the basis, plus rho phi dot U phi plus rho theta dot sine of phi U theta. Does it make sense? Do you see any errors? Does that have the dimensions of a velocity after all these calculations? Well, if this is a distance, definitely looks like a velocity. Distance, rate of change of an angle, that looks like a velocity. Sine of an angle has no dimensions. This is also 1/seconds, a distance, so that dimensions are fine. Does it also make sense? These are spherical coordinates, right? So if I start locking things into place, what do I see here? If rho is constant. If rho is constant, this goes away, right? That's the only term that will go away. There is no rho dot anywhere else, so the other two remain, and so I don't see any component of the velocity of P in the direction of the in the UR direction. So P at the most is moving on a sphere. It's as components of velocity on U theta and U phi, but nothing that goes outside of that sphere or radius rho. So that makes sense. And what else do you want to lock into a constant value? Say that you block the theta to a fixed value, then this will go away. You don't get any side. Same as with the cylindrical coordinates, you don't get any side component on theta. That makes sense. And the same with phi. You can do the same exercise. So that's a good sanity check, right? I may have some sign mistakes, but if I kept all the order of the vectors right, I shouldn't. So that's VP in A if I have cylindrical spherical coordinates. That's what we do. We draw the we've seen the sphere which represents Earth and longitude and latitude and height last time. That's actually what we're doing, except that what we usually do on this planet, we use the other angle here, right? So here I'm using the co-latitude, but that doesn't really change things much. They are pretty much the same coordinates, and that's what you get on your GPS. That's how you individuate objects moving on the planet. So what is left to compute is the acceleration now of P as seen by an observer in A as a function of these coordinates. And that's going to be fun, because the cross products become even bigger than this. So I don't want to erase the velocity. Let me just keep it up here, because I will need it. Vp in A is this u phi plus rho theta dot sine of phi theta. So these two things I will need. Okay? You can start telling me what I have to do here. I mean, I know where I'm going, but you can start telling me here. What is AP in A? No, just step by step. What is the definition of the acceleration of a point in a reference frame A? D, dt in A. Don't skip writing these things. Don't do it. It's not a good idea. It will not save you any time if skipping steps leads you to missing important things. So just write it. It's a good habit. So okay. Well, now I can do the transport theorem, because I have everything expressed in the basis fixed in C, right? And I am sitting in C. So this I can compute right away. ddt in C of Vp in A. I do have Vp as seen by an observer fixed in A. It's expressed in a coordinate system fixed in C. That's always the case. The first derivative of transport theorem is something that you can do without looking at the unit vectors. Just do the derivatives of the components, right? Plus omega Ca cross with Vp in A. And here the fun will start. Okay, so I think at this point I can probably erase the picture, because I really need the rest of the board. Are we all fine with this? Again, do I want you to memorize this? Absolutely not. You need to be able to derive this? Yes. I could ask you to do this in a test or something similar. Okay, so first term to compute is dt in C of Vp seen in A. That's going to be rho double dot ur plus rho dot phi dot plus rho phi double dot u phi plus, and this is going to be interesting. Okay, let's do it one by one. Rho dot theta dot sine of phi plus rho theta double dot sine of phi plus rho theta dot phi dot cosine of phi, and I'm done. U theta. Did I do this right? Derivative of product. Okay. And that's the simple part. Now the cross product is going to be, and I'm not going to write it here, I'm going to do omega Ca cross with Vp. So first vector cross with the second vector. Just to remind me. So let me not write those again. Let's just try to do the cross product one by one. So I'll go with the first term here and do the cross product with every other term of the velocity. So the first one gives me, I see a ur cross with ur, of course, goes away. Then we have an ur cross with u phi. That's a u theta. So that is, help me here, rho phi dot theta dot cos phi u theta. And then first with the last. UR cross with U theta. That's a minus U phi. So we get a minus rho theta dot squared cosine phi sine phi, right? Cosine phi sine phi, and what did he say? That it's a U phi, yes. Okay, and we're done with the first one. Second one, U phi cross with UR. U phi cross with UR is minus U theta, so that minus goes away. I see a rho dot theta dot sine phi. What do we say? U theta. Okay. Which one have I done? The first one. Still the first one. Second one goes away. Third one. U phi cross with U theta. U phi cross with U theta is UR. So the minus actually stays there now. Minus rho theta dot squared sine squared of phi UR. UR, right? Okay. So we're done with the second. Last one. U theta cross with UR. U theta cross with UR is U phi. So I have rho dot phi dot. U theta cross with UR, U phi. It's kind of difficult to do it on two boards. U theta cross with U phi. This is really the last one because the last one is U theta cross with U theta. U theta cross with U phi minus UR. Minus UR. So I have a minus rho phi dot squared multiplying, what do we say, UR? Okay? Do we all agree? So this is the second term, omega CA cross with VP in A, and this is the ddt in C of VPA. So this is what you have, this is the algebra that you have to do after you have formulated the problem, right? This is the important part. Figuring out the single ingredients is the important part. Setting up the problem is the important part. This is being careful doing the cross products. And doing it on 2 pages is probably easier than a board. You can do bookkeeping a little better, but that's how it is. So let's put it all together. Let's try to be organized here. So A, P in A using spherical coordinates is going to be equal to, let's see what we have in front of UR. I have a rho double dot. That's it here. I see UR here and here. So I have minus rho theta dot squared sine squared of phi. Let me erase the ones I have taken into account. And then I have this minus rho phi dot squared, and this is times UR plus, which is the second vector is this one. So I see U phi, it's rho dot phi dot plus rho phi double dot. That takes care of this one here. Whoops. Let's see, I see a couple of U phis here, minus rho theta dot squared, cosine of phi, sine of phi. That's the second one. And then rho dot phi dot. And this is U phi. Last one is this long expression here. Do we see similar terms?
Yeah.
This. This one? right? Twice this one. So 2 rho dot theta dot sine of phi and then I don't see any other similarities here, to be honest. Oh, yeah, that same. 2 plus 2 rho theta dot phi dot cosine of phi. Okay. And that's the last one. Plus rho theta double dot sine of phi. What a pain, right? This was painful. But this is something you're supposed to be able to do yourself. So I've done it for you once with these particular coordinates because they are used, because we use them all the time, because they are practically used. When you look at an object moving, you usually measure these angles and this distance, and you can compute the rate of change. So if you have a final expression like this, you can tell me north-south, away from you, what is the acceleration. You can tell me those components, and same for the velocity. So once you have these, you can practically on this planet measure these angles and rho that it's actually done. And you can find the acceleration and velocity of point P in your reference frame A, which could be the Earth. And again, forget about doing that with x, y, z on something which is spherical like the planet. No one talks that way about position and velocity and acceleration of a point around any planet. So these are practically used. You can do your dimensional check if these are all accelerations, if they are dimensions of accelerations. And again, I may give you just different types of coordinates, and you have to go through a similar exercise. So this was actually an example, if you like. It happens to be spherical coordinates, but this was a good example for transport theorem. So is everything starting to make sense here about the transport theorem, how to use it? Now, I commented the last time that things kind of get a little more complicated when the origins are not the same. So far, I've defined reference frames that have coordinate systems with the same origin. If you notice, my vector was always, position was always going from O to the point. I wasn't introducing any other origins. The most that we've seen is 2 rotations, like in this case, 2 angles. And so we're going to derive, because it's good to do it in a dynamics class, we're going to derive what is the final expression to compute the velocity of an acceleration of a point when 2 reference frames are involved and they both rotate and translate with respect to each other. But that formula that you probably have seen several times is not what we're going to use for the rest of the class. We're going to derive it, comment about it, because it's good to do it, because it's another exercise actually about transport theorem. But the final result is something where you would have to plug in vectors. And believe me, it's much harder to do that, even though you start from a given formula, once you're facing a problem, than actually solving the problem step by step, as we'll do. But let's look at what happens first. When you have, say, a reference frame A, so this point O is fixed in A, and I have defined, of course, my coordinate system in this reference frame A. And then I have another reference frame B, which in which I've defined a coordinate system whose origin is called Q. So this is O is fixed in Q. I'm sorry, Q is fixed in B. Okay, so this is B. When I do this, I don't mean to say that the axis of the coordinate systems are the frame. I'm just saying that this coordinate system has been defined in the reference frame. So there's no simple rotation involved here about one axis. They don't even share these points. There is no point that they share that can be fixed in both frames. So this is the most generic case. And say that I am looking again at a point P. And I want to compute, of course, its velocity and acceleration. And so now I have 2 observers, as usually, one in A, one in B. So the position of P with respect to O is, let's just call it R, RP if you like. I just drop the O. That's where you are, your frame A. And here I have the position of P with respect to Q. And I have also the position of Q, which is respect to O. But I'm going to drop the O part. So with this triangle, you can say that RP is RQ plus RP with respect to Q, right? Nothing special. Okay. Well, the same story goes for this case. I want V of P as seen by an observer in A, and the acceleration of P as seen by an observer in A. Because again, I may be actually sitting here. This is the frame where I would like to know how things are changing, but I'm actually sitting here. But I definitely need to know how B is moving with respect to A. So I know its angular velocity B with respect to A, and I better know how the origin is moving with respect to the reference frame A, right? So those are things that you assume you know. You need to know how the two reference frames are moving with respect to each other, otherwise you can't really go from one to the other one. So, okay, I'll just do it then. What is V P in A? Same. D dt in A of RP, right? So an observer in this reference frame here is looking at that point, and it wants to compute the rate of change of the vector RP. But if I break it down with that expression, this is also equal to d dt in A of RQ plus R of P relative to Q. Which is d dt in A of RQ plus d dt in A of RP relative to Q. So here the thinking comes into place. What can I call this term here? What is actually this term here? d dt in A of RQ.
Translation velocity.
It's the velocity of Q in A. Again, you need to know what we've seen so far is reference frames that rotate with respect to each other. So we assume that somehow you can compute the angular velocity between the two. So likewise here, not only you need the angular velocity between the two, you also need to know what the origin of the second one is going away, is moving with respect to the first one. Otherwise, you don't know the motion between the two reference frames. You don't have enough information. You cannot relate them to each other. So this is the velocity and observer of point of the origin of the reference of the coordinate system fixed to the reference frame B as seen by an observer in A. You better know that. You need to have that. Okay, so we just call it that way. V of Q in A. That's what it is. Now, RP in Q, probably that vector RP in Q is something that the observer in B can express. And so here we can apply the transport theorem. Does it make sense? D dt in B of RPQ plus omega BA cross with RPQ. Think about what we said last time. When you start having roto translations of reference frames, you start having more vectors, right? If you ignore this, you go back to, well, the origins basically collapse. Q goes to O, and you just go back to the transport theorem only for that term, right? That's exactly what we've done so far. Okay, so what is this? What can I call that term? Can I give it another name? It's the velocity of P with respect to Q as seen by an observer in B. The observer in B can measure that, right? So that is something that the other observer can determine. So V of P with respect to Q in B. That's what it is. Plus omega BA cross with RPQ. That's pretty simple. We stop right here. This is how you relate the velocity, this is how you compute the velocity of P as seen by an observer in A when you have another observer in B, which is a frame roto-translating with respect to A. You will have to know the velocity of the origin of that frame as seen by the observer in A, the velocity of p with respect to the origin of the B frame as seen by an observer in that frame plus this cross product. So this is the only piece that I'm adding here so far. And that's exactly what you're going to do in a problem. Again, I don't think we're going to have really time for problems here, but we'll stop here and we'll see how we actually do it in reality with an example next time. So this will be the velocity. I'll write it, just erase top and just write it up here. Okay. VQ in A plus VP with respect to Q in B plus omega BA crossed with RPQ. And I'm not going through these calculations just to waste time, because I told you that we're not really going to use these formulas in the end. It's because there is also a definition that comes out of this procedure, the definition of angular acceleration. So it's important that we do it at least once. Okay, so this was velocity, acceleration of P in A, d dt in A of this vector, right? d dt in A of Vp in A is d dt of all this. So it's d dt in A of Vq in A plus d dt in A of Vpq in B plus d dt in A of that cross product. So omega BA cross with RPQ. Okay. Can someone start helping me with these terms? Let's start with this one. d dt in A of the velocity of Q as seen by an observer in A. What is that? So the use of transport theorem or not doesn't need to become something that you just do it mechanically. You do it when there is the need to do it. So in this case, what is this? It's the acceleration of Q in A, right? Again, I better know that. Otherwise, I can't relate the reference frames between each other. A of Q as seen by an observer in A. That's it. Just call it that way. Second one, I probably have to do something else. The second one is the velocity of P with respect to Q as seen by an observer in B, but I want the rate of change of that vector as seen by an observer in A. So I probably should do the transport theorem right there, right? So d dt in A of V P with respect to Q as seen by an observer in B. So if I apply the transport theorem, is d dt in B of Vp with respect to Q in B plus omega BA cross with the same vector. Now here I can start giving some names. Compare these with these, right? Compare this rate of change here. Look at the superscripts and compare to these same superscripts. I can call it somewhere else. Acceleration of P with respect to the point Q in B. So the guy that is sitting in B is sitting on the point Q. That's its origin. It's looking at P and it's measuring velocity, which is this, and also an acceleration, which is this other vector here. Okay, and the rest, the second one remains as it is for now. Actually, will not change. Okay, that takes care of the second one. Then the last one is the, say the more complicated one already. Okay, d dt of omega BA cross with Rp with respect to Q. So it's a product, it's a cross product, but the same rule applies here. I have to do the derivative of the first cross with the second plus the first cross the derivative of the second. So I see a d dt in A of omega BA cross with Rp with respect to Q plus omega BA cross d dt in A Rp with respect to Q, right? Make sense? What is this? Alpha? Can I call it angular acceleration, just like that? I mean, we've been saying that rates of change do depend on the reference frame, right? So can I just take that and call it something?
Well, we showed that the angular velocity beta A is equal to the negative
Right. Okay.
angular velocity A p. So perhaps there's some kind of relation like that. So we could show that the angular acceleration is the same.
So we did demonstrate this, right? That omega b with respect to A is equal to minus omega A with respect to B. And so the suggestion is using this to demonstrate that what is it that I want to demonstrate? If I can call this some other vector alpha, I either express it specifying which reference frame that vector is rate of change is computed, or maybe I don't need to do so. So d dt in A of omega b A. I want to define it as, and this is what I will do, alpha BA. But can I do that? I mean, if what if this is not A, this is another reference frame? What do I do in that case? Transport theorem. So if I do express this the following way, d dt in B omega BA plus omega BA cross with omega BA, guess what you get? This is 0. And so it doesn't really matter in which reference frame you take the rate of change of the angular velocity. So you can drop this. Doesn't change. And so I can actually define it, getting confused here with all these vectors. I can define these as simply d dt without having to tell you which reference frame is doing it, omega BA as alpha BA, or angular acceleration of B in A. In A. Okay. So I don't know, let's see where I am here. I need to save this piece here. Actually, I should probably write it here. Okay, so we said that this has become the acceleration of Q in A, plus we took care of this term, and that's what remained here in the middle. It's A P with respect to Q in B plus omega BA cross with V P with respect to Q. So I can erase this, get it out of the way. I was taking care of the last term, so it breaks down in two pieces. The first one becomes, I don't need this anymore. So we're going here now. First one I said it's alpha BA cross with R P with respect to Q. Okay. First one is taken care of. And then I have omega BA cross with d dt in A of these are p with respect to q. What is that? I think I've done it before. Look at that formula here. You should remember where this is coming from. Rp was Rq plus Rp with respect to Q. All I've done is taken the rate of change of all that, and the rate of change in A of Rq gave me this first term. The rate of change of P with respect to Q in A gave me all this other thing. So that's exactly what I have right here. So d dt in A of Rp with respect to Q is Vpq in B plus omega Ba cross with Rpq. This is painful, right? This is more painful than the other one, probably. That's why I don't think you should use it. But at least it allows me to define the angular velocity. But again, this is not the only way to address problems where the frames don't have the same origins. Okay, so this is the first plus. I have omega Ba cross with Vp with respect to Q in B plus omega Ba cross with Rp with respect to Q. Okay. I think I have everything I need. I need to add this to what I have there. Alpha Ba cross with Rp with respect to Q plus omega Ba cross with Vp with respect to Q in B plus omega Ba cross with double cross product here, omega Ba cross with Rpq. And if you want, you can write it one more time, AQ. So we can give names to all these terms, AP with respect to Q in B. I have twice this cross product, right? Plus 2 omega Ba cross with Vpq. What did I drop here? The B. The B in B, okay, plus alpha Ba cross with Rpq. And the last one. Bless you. Careful here, there is a specific order when you do this. You cannot do this cross product first, of course, and then this, because that's obviously a 0. So it's always a good idea to keep these brackets or parentheses here. You first do this cross product, then what you get, you do another cross product. Okay, so this is the final formula that we've probably seen for years and years, or at least you may have seen it at least once in other classes. The acceleration of a point P as seen by an observer fixed in A is given by the acceleration of the origin of the, call it the moving frame. We always tend to give a name to a frame saying this is my fixed frame, this is my starting frame, and that's the other one that is moving. All motion is relative, but let's say that our main frame is A, so the other one that is moving is B, if you like. But so this is the acceleration of the origin of the moving frame B, the acceleration of point P with respect to Q as seen by an observer in B. This is called, what is this called? Coriolis acceleration. This 2 omega cross with Vp respect to Q in B. This, it's called Euler acceleration, alpha Ba cross with Rpq, and this is called centripetal acceleration. And this is terrible. I mean, you can use it. If you want to use it for every problem that you're given, you need to first, of course, figure out what the reference frames are, and that's always the case. You have to do it regardless. But then you have to figure out all these vectors here. And you need to be very careful how you do it, in which reference frames they are computed and expressed. You don't really have much insight by just blindly applying this formula. And most of the times when you do, you don't get the right results. At least that's my experience. You don't really need to go through this huge thing. You don't need to memorize it. There are other ways to solve problems when the origins are not the same. And really what we are doing with all these huge expression here is nothing else than writing the, so other than AQ, this is really the acceleration of P with respect to Q as seen by an observer in A. That's what it is. Do we agree? So in the problems that we'll see, this will be probably quite simple to compute. Well, this will just case by case apply the transport theorem. We'll first compute the acceleration, and the same goes for this one. This second term is nothing else than the velocity of P with respect to Q as seen by an observer in A. So in the problems we'll face, we'll compute this first with the transport theorem, then we'll do it again to compute this term. We don't need to memorize this formula. But that's what most of the dynamics classes and books give you. And then again, one thing is that you need to memorize it. The second thing, you need to be extremely careful plugging in the right vectors. And I don't think that's the right approach, especially for a graduate class. You don't want formulas where you plug in vectors. You compute those vectors. So we'll basically see problems where you attack computing these vectors directly, which is basically doing what I've done here symbolically, but again, you don't need to memorize the formula. And the problem that we'll see, I really don't want to start it now. I don't think I even have it here. Let me see. Well, I'll try to draw what I remember so you can start thinking about it. It should be something like this, where we have two uniform slender rods of length, I don't know, L1 and L2. This is point O, this is point Q, and this is point P. Call this angle theta 1, and this other angle theta 2. Again, I'm drawing by memory here. I don't know exactly what I'll call these lengths and angles, but it's more or less the same concept, and I want to compute. So this is the ground, right? Of course. And I want the velocity of P with respect to the ground and the acceleration of P with respect to the ground. And if you start thinking step by step about this problem, the first thing you do is define the reference frames. And how many do you think it makes sense to define here? 4 reference frames? How many rotations do I see? 2 rotations. So with problems with 1 rotations, we usually have defined 2 reference frames, right? So this is probably 3 is enough, right? I mean, and if you think about physical objects, this may be the floor. This is 1 bar, and this is another bar. So each rigid body, we're not doing rigid body yet, but that's a rigid body or reference frame. We said it's the same thing. So 3 reference frames. So say this is ground, arm 1, arm 2. Well, if you define this as reference frame 2, arm 2 as the third one, well, this doesn't have the same origin as arm 1. So this is one of those cases where they don't have the same origin. And so start thinking about how you would attack this problem. I don't advise you to waste even any seconds of your time try to look at that formula and apply that formula directly. It's what we'll see next time, I guess. All right, thanks.
Theta 2 is the angle